Welcome back, my dear friends. A very good morning, good afternoon, good evening, wherever you are in this part of the globe. And as you know, this is the DADM 3 course, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And as you know, this DADM 3 course, like DADM 1 and DADM 2, is total duration is spread over 12 weeks. And as you can see, we are in the 5th week, 23rd lecture, which is with the 3rd lecture in the 5th week. And this total contact number of hours for this DADM 3, like DADM 1 and DADM 2, is for 30 hours, which when converted into number of lectures is 60, because each lecture is for half an hour. And each week, considering this is the 5th week, we have already finished 4th week. That means 4 weeks. So, each week we have 5 lectures of half an hour each, and after each week we have an assignment. So, you have already completed 4 assignments, and we are with the 23rd, 24th and 25th lecture, you will go and take the 5th assignment, and after the whole course you will basically take the final examination. So, if you remember, we were discussing about the simplex method, and I gave you how the solution basically changes depending on the entering and exiting variables, depending on whether you are trying to do the maximization problem or the minimization problem. And based on that decision, like for the maximization problem, you bring everything onto the right. I would be repeating many things time and again, please bear with me. So, you take the maximum in the negative sense, because it's you have brought it onto the right hand side, that will be the entering one, depending on the fact that it will increase the objective function maximization to the maximum degree or maximum quantum, and that would basically become the pivot column based on which you will rotate or basically do the conversion, and the pivot row would be the one for that variable which will leave the system, such that in the maximization problem the decrease in the objective function would be the least. Hence, we take the ratio on the right hand side, which is the b value. I will always consider that as the b value, b vector, divided by its corresponding coefficient, that is the unit based on with b divided by its corresponding cell, will give me per unit reduction in the objective value if it is a maximization problem, and that would be the exiting one. And if there are more than 2 contenders for the entering one, you will take both of them, but also consider that the ratio for which it is minimum for the exiting ones. If one we can find out which minimum, we will take that. If both of them are the same, then obviously you have to basically use one of them, but intuitively it means that there are 2 different corner points depending on which you will get the maximization concept. You continue doing this, observing the fact that the metric corresponding to the basic variables which are there on the leftmost column, those corresponding cell values would be 1, rest would be 0, such that when you put the basic solution to the one value which you have on the right hand side, that will give you those exact solutions, such that putting them in the objective function, whether there is a slack or the surplus or the actual variables, will give you the objective function maximum. So, we saw that it changed in our last example, it changed from 0 to 30, from 30 to 36, and after 36 obviously any negative values for the entering variables were not there. So, here to basically stop there. And the minimization problem, obviously when I talk about the minimization, is just the reverse. That means, if it is the minimization one, you are trying to basically find out that the fall, the decrease in the objective function would happen the highest, increasing whatever it is, and exiting one would also be considered likewise. And again, contenders for 2 or more points which are entering and exiting would be basically be clarified, that as at the 2 corner points you can have same solution for 2 different values of the corner points. And for the unboundedness, we discussed that as you keep changing the entering and the exiting ones, they would be not going out of those x1, x2, x3, x4 whatever these variables are, depending on how many slacks and surplus which you have and how many actual real variables which you have, but the z value will be unbounded. It will keep increasing for the optimization problem, it is maximization, and in the case if it is minimization, it will keep decreasing. So, we were discussing the last day on the 22nd lecture. So, what is the directions we considered? So, directions obviously what I have been discussing time and again are the same thing which have been written in words. So, the simplex directions are constructed by increasing the single non-basic solution. Now, remember the important fact is that it has to be a basic feasible solution. Feasibility is very important, because if you find out the constraints and the point satisfying is one of the point which is actually plausible, but is not inside the feasible region, then it does not make any sense in trying to solve it. And we have considered very simple examples earlier. The single non-basic variable leaving would be leaving such that other non-basic solutions, basic variables remain unchanged. So, which is very important, because when you are changing from one corner point to the other, we are only considering that there is a change of one variable at a time, because the movements would be happening in such a way that you would consider the movements taking place such that if in the tableau if you saw, so there was only one variable which is entering. So, one enters, obviously it will push out the other, so that will be only single one. So, the movement of the corner points are such that there is only one change which is happening in the variables, point 1. Point number 2, you should also remember that when we are considering the entering and the exiting ones, we are considering the simple concept as I mentioned is dy dx will take in the maximum and the minimum direction depending on whether it is a maximization problem or the minimization problem. But this dy dx I did not specify, it should be the del y del x, that is the partial differentiation based on the fact that when we change one of the variables with respect to the others being kept fixed, we are trying to find out the rate of change of the objective function, which is the maximization or the minimization problem based on only one change. That means, one variable comes in, another variable goes out. We are not going to consider more than one in the simplex method. So, that is very important. So, there the point it mentions the simplex direction are constructed by increasing a single non-basic variable which was not there in the basic, obviously it will one will be coming inside and one will be going out, such that other non-basic would be kept unchanged, because they keep changing. Obviously, you cannot find out in which direction the rate of change is the maximum or the minimum for the problem of optimization. And we will compute the unique corresponding change in the basic variables as we did, like x1 comes, x3 goes out, or x3 comes, x4 goes out, whatever it is, irrespective of the fact whether x1, x2, x3 are the slack or the surplus or the actual variables, whatever it is, that would depend on how the problem construction and how the procedure of solving the problem occurs. So, the corresponding change in the basic variables would be necessary to preserve the equality constraint, because remember when we have constructed the tableau has been constructed in such a way that addition or subtraction or plus or a minus whatever we have put for the slack and surplus have been done in such a way the equality sign holds for the right hand side, which is the b values. So, if somebody is entering, somebody is going out, that equality is always preserved. If not, what the problem is, if you remember in the last class I mentioned that the values of at any stage when you stop, you take a snapshot, the variables which are there on the left hand side, these are the corresponding coordinates for that corner point. So, when you equate them to the right hand side, which is b, corresponding to the fact that you have obtained the identity matrix corresponding to those x values only, equality sign would mean that those are the exact values of x's, such that when you put them and find out in the objective function, they would give you the exact value of the objective function at that point. So, as you keep moving, the equality sign is it holds always, and the new sets of x's would be given by the new sets of b's which you have. Once you find out these x's, you put them in the objective function, you have already got the objective function which is maximization or minimization as it is, and then you decide whether you want to proceed or stop. If no component is negative in improving the simplex variable concept, which is true where you, because you are bringing from the left hand side at the current basic solution, then the solution can be, if the non-negative ones are not there, and if you think that the sign is not changing and one would always enter and one will always go out, and if this cycle continues based on the fact that the objective function will keep increasing, which means that you are slowly tending to move more inside the first quadrant away from point 0, such that you would not have any unique solution, it will be an unbounded one. Just reverse the concept. If you go into the third quadrant, or you basically, I am trying to solve the problem considering the dual problem, you will also see that as you keep increasing or decreasing as the case may be, the objective function would become more and more negative, hence the minimization problem would basically mean that you basically go to minus infinity. Now, the simplex method for the initialize the overall algorithm works very simply. What I have been talking about is in words, I will just mention them in a stepwise formulation. So, whatever I discuss is just a formalization of the procedure how you proceed. So, we will initialize. So, what you want to initialize is that you want to find a point from where you want to start. So, what is that point? That is a basic feasible solution, which I told that in many of the cases is the point 0 based on which you can proceed, provided it is feasible. So, in initialization, choose any static feasible basis and construct the basic solution x naught, which is the iteration point at t is equal to 0, considering that you are starting your overall process at t is equal to 0, and set the index at t is equal to 0 and then move. So, t is just a counter, it is nothing to do with time. So, you will basically change. So, as you are moving around the counter around the corner points, t will change from 1 to 2, 2 to 3 and so on and so forth. So, the simplex direction occurs like this: construct the simplex direction, in which direction you will move, associated with, here the important point is associated with increasing each non-basic variables and compute the corresponding reduced cost. So, reduced cost in the sense that you will try to find out that as you are moving, remember one thing, this is important, as you are moving, you are trying to move in the maximum possible direction. Now, the maximum possible direction would always be where the del y del x or del f del x, f is the objective function, x is basically any one of the x's based on which you will proceed, is basically maximum or minimum depending on how you are looking at the problem, for the maximization problem and the minimization problem. So, as that occurs, when you go to the next point, the contenders or dy dx would definitely be there in any one of the x's, but the rate of change of the function would now basically be increasing as a decreasing rate. So, basically you are trying to slowly reach the objective function which is maximization. So, you will keep increasing in this, but the rate of change of this equation would happen at a slower rate. Now, here I will just step aside and tell a few facts about the initial assumption which you took. If you remember, in linear programming we assumed that there is a linearity in the addition and subtraction of the object of the variables. That means, one unit increase, one unit decrease in the variables x's, whatever the x's. When I mention the word x's or b or the y's, when it is a dual problem, remember I am talking about the vectors, because x is a set of vectors, similarly y, similarly b, or a is a matrix. So, any addition or subtraction of any one of the x would always keep increasing or decreasing your objective function by the same quantums. That means, in general we are not considering a decreasing return to scale or an increasing return to scale, as they may be the cases in one of the method, which is DEA, data envelope analysis, which we have considered a long time back in DADM 2. So, as we construct the simplex direction associated with the increasing each non-basic variable, and we will compute the corresponding reduced cost and produce in the direction where the increase or decrease is happening the most or the minimum. Now, you want to check the optimality. So, if no simplex direction in the direction where we are moving is improving, that means it is not giving us a higher value of y or z as the objective function. That means, if you remember, we took the value of 30, then it increased to 36. Now, after 36, if you saw, technically there was no entering variable. Consider that we do not consider, we ignore that. We forcefully bring one of them into the as the basic solution and forcefully take one out in the basic solution which is optimal at the point of 36. Say for example, we forcefully bring one and forcefully take out one. The result would be 0.1, the objective function will decrease from 36, 0.1. Point number 2, that it would be in the case that the slacks and the surplus which could have been 0 in the actual theoretical sense would now no more be 0, because there would be some extra amount for either production plant 1 or plant 2 or plant 3 or machine 1, machine 2, however the problem has been framed with the constraints, there would be some extra amount left, or extra amount has not been utilized, or it is still to be unutilized. So, those would be coming into the picture, because in that case the variables based on which you want to optimize would not reach their actual maximum value in order to give you the maximization or the minimization problem. So, if no simplex direction is improving for a maximization on the minimization problem, then you will stop, you will not proceed further, else improving the simplex direction till it is possible, you will continue. So, you will check, if it does, improve, continue improving, find out the x the point means the vector, find out z. Now, after you find out z, go to the tableau, double check, is there an entering, is there an exiting, answer is yes, do that, find out the value of z. But obviously, unboundedness and all these things properties would be checked, but you will continue doing that till you reach the unique solution, stop it. Step size, if there is no limit on the feasible moves in the simplex direction, which is important, because in which direction you will keep moving, that is not being given by the tableau, final tableau which you get. So, each time you have some negative values in these, in the topmost 0th equation, and it says that somebody should enter, somebody should go out. So, if it keeps happening, you will find out the variables, basic variables and the optimal case, there is no optimality here. So, the rotation or the change of these variables will be happening time and again, which will point to the fact that your objective function will keep increasing or keep decreasing depending on the maximization and the minimization problem. So, it says that if there is no limit on feasible moves in the simplex direction, then stop as the solution is unbounded, both in the negative sense and the positive sense, else choose the leaving variable and the entering one, and basically repeat the process accordingly. Now, we will consider that if there are with lower bounds and upper bounds. So, if you remember in the initial case of the maximization minimization problem, we had the example where x was over all greater than 0. So, which means that if you consider the minimization and maximization bounds, so here the problem is like this, you want to minimize or maximize Cx. So, why I am saying Cx, these are all vectors or matrices, that is why they are bold. So, if I consider Cx, Cx is basically, I would use, so this is C1 x1 plus dot dot plus Cn xn, and here we are considering, because as there is equality sign, we are considering the slacks and surpluses are all subsumed in this equation. So, it may be possible out of this n is 20 considered. So, the first 10 are the actual variables, while the next 10 like 11, 12, 13, 14, 15 out of the 20. So, these 5s are all slacks and 16, 17, 18, 19, 20 are the surpluses. So, all these are subsumed here. Now, why this equality sign? Because the moment I said that all are subsumed in this equation, it means that even if, which I will erase, let me use So, even if they were this, so these are bold, remember A and X are bold, or this, so all of them being converted using the slacks and the surpluses to the equality sign. So, you have now A x1 is greater than is equal to B and A x is equal to B depending on slacks and surpluses how they have been added. So, obviously, it would mean the matrix of size A is m cross n, where the rank would be the minimum of m and n, and we are taking the column operation accordingly. So, rank is the lower of one of the minimum of them. And if you remember, you had x's greater than 0. So, now you have basically x's are between L and U, lower bound and upper bound. So, obviously, x1, okay, if I write it here, so this would be A11 till A1n, AM1 till AM into x, which is, so there are n number of variables obviously. So, you have to need multiply, that is equal to, so initially what was that, m cross n for A, n cross 1 for x. So, m cross n into n cross 1 would give you m cross 1 for B. So, the matrix multiplication is valid. Now, if I look at the bounds, so the bounds are like this. Technically, we already had all greater than equal to 0. So, what we now actually have is L1 is for the first one, L2 is for the second one, similarly last one. So, all these things would basically is given by the equation here. So, what can be the plausible formulation, like say for example, you are in a factory and it says that in the factory your total number of production of X, even if the constraints are such that you cannot produce more than 20 of the first paint, and then so the first paint has to be produced in quantum of minimum of 5. That means 5 liters, 5 tons, 500, 1000 liters, whatever the case be, you have to produce for the paint one in the paint manufacturing process, and you cannot produce more than say for example 10 tons or 10,000 liters, whatever it is for paint one also. So, in that case x1, which is the variable for paint 1, would be bounded between 5 and 10. So, it will be x1 is greater than equal to 5 is less than equal to 10. Similarly, you will have for paint 2, paint 3, so on and so on, depending on that you can have the constraints also. So, now the simplex method with the lower and the upper bound. So, in the initialization, choose any starting feasible basic solutions with initial non-basic solution for the upper and lower bounds. So, you will basically consider the upper and lower bounds in such a way, so that they would basically give you the feasible solution. That means, what you are doing is that you will have the feasible set, which is fine, but you choose the upper and lower bound, or you consider the upper and lower bound in a sense that they would be one of the sets in the as the starting basic feasible solution, because obviously if it is a basic feasible solution, it may be possible to is the optimum solution. Now, we will consider the basic of the current representation to find the direction of the movement. So, the pricing would this pricing is that as you bring on to the left hand side, the positive value and the negative value would give you the overall importance. So, the optimality, so if no improvement and the rule is found, then you will stop the iteration process, else you will choose the entering non-basic variable. So, again the same concept, they would be entering non-basic, it will throw out one or push out one of the basic existing one, and replace the entering one, replace the exiting one, and that will become the new basic solution. And then you find out the values of B would be recalculated using the pivot column, pivot row, the pivot cell, based on which you do the transformation. As you are doing that, your zeroth equation, which is corresponding to the z value for the minimization, or if it is w for the z value for the maximization, and if it is w for the minimization, you will recalculate it and do the calculations again. So, if no improvement rule is found, then stop, else choose the entering basic feasible basic non-basic variable and decide on exiting variable based on the rule of maximization and minimization, and you will continue that. You will construct the direction of the simplex using the representation as you have done it. So, you will basically consider entering, exiting, but also consider that at what point you will stop, that will be dictated by the entering and exiting one, whether they are actually feasible, because if there is no non-negative one, then obviously it will mean in the case of maximization there is no one who would replace any one of the basic variables in order to improve the objective function. You will determine the maximum feasible step as allowed for maximization and minimization in the same way. Find out the rate of change of the function. Again remember, it is del y, del x, del f, del x. So, x is basically the vector. You will consider del y, del x1, del y, del x2, del y, del x3, del y till del xn, and check the one for which the rate of the increase of the function is the maximum. That is why you are taking the value of the minus negative being possible, because if you keep all of the other variables fixed, then you will try to find out that as one unit of x1 or x2 or x3 changes, what is the additional profit which is going to come to the objective function, by what unit it will change. So, that is given by the value of 5 or 3, whatever was there in the maximization problem. So, you will determine the maximum feasible step as allowed for the maximization and minimization, and continue considering the exiting ones based on the fact that which one will you leave. So, that will leave which will basically bring down your objective function the least if it is an optimization maximization case. You will compute the new solution based on the change in the objective function for the maximization and minimization, and you will keep computing it in the same way as you did for the Tableau. You will keep computing it till it is possible to consider that there is one entering and one exiting variables, but obviously look into the fact that entering and exiting are not happening in such a way that your actual objective function is unbounded, and obviously in that case it unbounded means that it will keep increasing till infinity, both in the positive sense or the negative sense. Now, this generic optimization problem I have already stated. I will state this in very simple terms. So, here the reason why I am stating is that in all of the problems I have been stating that this parameters based on which we are trying to optimize are fixed, but they need not be. If they are not fixed, which is what? Your constraints may change. Like say for example, if you consider machine 1, your actual utilization is 8 hours. So, what if it becomes 9 hours? So, if it is deterministic, we solve the problem accordingly. If it is non-deterministic, we will solve the problem in a likewise manner. So, again I will state you have an optimization problem with repetition of 1 only if I is 1. In the first set you have a deterministic one, second set you have a probabilistic one, and we will consider the solution in such a way that it will be possible for us to find out the concept of the shadow prices and the slacks and the surplus in such a way that we can comment intelligently what is going on in the simplex method. With this I will close this 23rd lecture and continue more discussion along the process as we proceed for the simplex method. Have a nice day and thank you very much.